Okay, the question asks the following. The thermal emission of the human body has maximum intensity at a wavelength of approximately 9.5 microns. What photon energy corresponds to this wavelength? We're going to make that part A of the problem, and we're going to add a part B. And the part B we're going to ask is this. If all of the photons are emitted at this wavelength, how many photons per second would the body emit? That's another calculation that we can do. Well, the first part of the problem just is a straightforward conversion between photon wavelength and photon energy. And the basic relationship we have that joins those two is this. The energy of a photon in electron volts is equal to 1240 divided by the wavelength in nanometers. Now, to use this, we have to convert the wavelength into nanometers. We're told that the wavelength is 9.5 times 10 to the minus 6th meters. That would be equal to 9,500 times 10 to the minus 9th meters. And so the wavelength in nanometers, 9,500. Given that, we can calculate the energy of the photons in electron volts. That's just 1240 divided by 9,500, clearly less than 1, as we'd expect it to be, 0.13 electron volts. And that's the answer to part A. And that number is quite reasonable because we know this number should be significantly less than the threshold for you to be able to see it. And the energy for photons to be able to see it is something like about 1.8 electron volts. So this is far beyond the range of what's visible. But we know that that's true. But now let's take a look at part B. How many photons per second would this correspond to? Well, we know that the body emits about 800 watts of thermal radiation. That's something we've done a couple of times. That's 800 joules per second. So to make this calculation, we need the photon energy not in electron volts. We need it in joules. So we need to convert this number to joules. To do that, we divide by 1.6, we multiply by 1.6 times 10 to the negative 19th. And that is the conversion factor between electron volts and joules. That's also the charge on the electron. And so we get the energy in joules of the individual photons is 2.08 times 10 to the negative 20th joules. So we have this many joules per photon. The body emits this many joules per second. And so to compute the number of photons per second, we just take the joules per second divided by the joules per photon, and then we get photons per second. 800 joules per second divided by 2.08 times 10 to the negative 20th joules per photon. And think about how this cancels out. Joules cancels. Photons is 1 over this is in the denominator, so it goes to the top. And so we end up with 3.85 times 10 to the 20th photons per second. And that's the kind of calculation we're going to do quite a bit. It makes sense just thinking about it. This is the number of joules per second. This is the joules per photon. Divide joules per second divided by joules per photon, and I get photons per second. But it makes sense if we sketch it out this way. And we expect this number to be large because the individual photons don't have much energy, and the amount of energy that's emitted, 800 watts, 800 joules per second, is quite large. So this number we expect to be quite large, and in fact, that's exactly what we find.